Yo, this is Celso Batalha. So let's go through the quiz number 2. So let me bring this in. And that one. Okay, so according to Newton's second law, remember that one? Sum of forces equal ma. So, and this is the net one. So according to Newton's second law, does the direction of the net force always equal the direction of the acceleration? Yeah. So look, they have a vector here, which is the net to have another vector. So they should um, have the same direction since uh, the acceleration is being multiplied by the scalar. So let's see. A, sometimes the direction, no. Yes, the direction of the net force will determine the direction of the acceleration vector. Mass is a scalar constant. Yeah, that's it. B is the right one. It depends on the number. Nope. No, the direction of the net force is nope. Nope, 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 nope. So the best probably supporting argument is if you have a vector b that is equal to a number like number c multiplied by another vector d, right? So let's say you place c equal to, say c equal to. Now, if d is this vector, then the vector b would be this thing here. That's your b, which is twice the previous one. Okay, same direction. Now, when constructing a free body diagram, why is it a good idea to choose your coordinate system so that the motion of an object is along one of the axes? Well, yeah, I think you guys saw that in the inclined plane. The inclined plane, you have a bunch of forces, right? You might have a bunch of forces, but we set the x-axis along the direction of the motion y. Well, because if we do that in any other direction, in the case y, the acceleration should be equal to 0 because there is no motion in the y direction, right? The motion is only in the x direction, so that is going to be equal to the net force in x divided by the mass. So it makes the problem more treatable and easier if you choose that way. So again, if you know the direction of motion, just set one axis there. So automatically all the net along a perpendicular direction should, or normal direction should cancel out. Adam drops a ball from rest from the top of a building. So let's make our building here. Adam. At the same time, Bob Stroll, so Adams, and Bob throws a ball horizontally from the same location. So Bob takes a ball and throw like this. Okay, that's Bob. Which ball hits the ground first? Well, believe it or not, they will hit the ground at the same time. Why? Because see, for Adam, y final, which is 0, right? Minus the height of the building, which is the initial position, is equal initial velocity in y, which is 0, versus time, minus 4.9 t squared. So for Adam, h divided by 4.9, this is for Adam, is equal t squared. And then you can find your time. Now let's do the same exercise for Bob. For Bob, it's absolutely the same thing. The initial position or the final position, in fact, this is final. Sorry about that. Final position, right? So this is final position when the ball hits the ground, right there. And for Bob, it go like this, right there. In fact, the initial velocity would be like this. Now for Bob, it throws horizontally, right? So which means the initial velocity in y. Man, what is going on with me? The initial velocity in y is equal, the initial velocity in y is 0, right? It has only an initial velocity in the x direction. It has v naught x, but doesn't have a v naught I. The projection of this initial velocity in the y-axis is 0. So when you set the same equation for Bob, what you got is final position minus initial position is equal v naught y, which is 0, t minus half 9.8 t squared. So the time is going to be the same, right? The equation is basically the same. So you find your h for Bob divided by 4.9 is equal to t squared, and the time is absolutely the same. So, and that's what we have been emphasizing in the classroom. For a projectile motion, the y direction is pretty much a free fall type of situation. An object travels with a constant acceleration for 10 seconds. The vectors in the figure below represents the final and initial velocity, determine the average acceleration. So the definition of average acceleration is final velocity minus initial velocity. Just follow the cookie recipe. Now you have to write down your final velocity as being a projection vector. And V initial is equal. Now when you project V initial in x is positive, right? Plus 20, same one, 20 cosine of the angle between the vector and the x is 60, but the projection is negative. So minus 20 sine of 30 j hat. So that, therefore, your acceleration, which is this vector minus this vector, gives this is I hat. So when you subtract v cosine theta no, wait a second, and this is 60. Sorry about that. This is 60. Cosine of 60, and this is 20 sine of 60. All right. So the acceleration is going to be 20 cosine of 30 minus 20 cosine of 60 I hat minus better saying plus 20 sine of 30 minus become positive sine of 60 j hat direction. All of this nonsense divided by the time. Do I have time? Yeah, 10 seconds. Okay. And then you operate that in your calculator. Now, determine the net force on the object in question 4 if its mass is 10 kilograms. So it's kind of a based on what we did over here, right? So we have the resultant acceleration. Where is it? Right here. So we have the resultant acceleration. So the net force. Is equal mass times acceleration. So that would be equal to 10 kilograms times whatever you got from here. Okay. 6. Soccer ball is kicked with the initial velocity. So you put a little axis and then you have an angle. This is your initial velocity. And the angle is 30 degrees. So basically the soccer ball is going to go and then looks like air resistance is doing some trick here. Okay, so it goes, the magnitude of this vector is 24 meters per second. The angle is 30 degrees above the ground, or the velocity vector, the ball, when it's 1 meter above the ground, so 1 meter. So basically, you want to find the velocity here and the velocity vector there. Well, projectile motion, what do? X component, and then you have y component. Now, in this case, it's always good to start preparing your velocity in x and y, the initial velocities in x and y. So this is your v naught, right? And what you want to find your v naught x, and you want to find your v naught y. Your v naught x is equal to 24 cosine of 30, and your v naught y is equal to 24 sine of 30. This is in meters per second. And another characteristics of projectile motion is v naught x is always the same. What changes is your v naught y. So the only equation you have here is x. And let's set the initial 0 for x and 0 for y. So x is equal v naught x t. So x is equal 24 cosine of 30, whatever time it is. So that's the only thing I have in x. In y, probably we want to need y because we want to find the velocity at 1 meter. When it's 1 meter, so there is a time that it takes the ball to go all the way here, and another time that it takes to go all the way there. So it might end up with 2 good times to deal with. So let's do that. So final position minus initial position is equal v naught y t minus 4.9 t squared. Okay, that's the basic equation. Final is 1 meter, initial is 0. So this is 1, right? Is equal to v naught y, which is 24 sine of 30, versus time minus 4.9 t squared. And then we find ourselves on a second degree equation that is 4.9 t squared. I multiply every one by minus 1. I don't like to deal with negative signs. Minus 24 sine of 30 is 0.5, right? So it's 12. Put 12 right there. Minus 12 t plus 1 equals 0. So t is equal 12 plus or minus square root of 144 minus 4 times 4.9 times 1 divided by 9.8, which is 2a. So this is square root of. So let me calculate this. I don't have a calculator here, do I? Use this thing here. So that is equal to square root of 144 minus 4 times 4 times 4.9 and equal to 12 minus this parenthesis divided by 9.8. This is the first time, and the other one is equal 12 minus or plus this divided by 9.8. So those are the two times that I got. So time one is equal, time two is equal, time one is equal, what is it? Okay, no, what is it? That's it. Yeah, time one is equal to 0.86 seconds, and the time two shall be 2.36 seconds. 2.36 seconds. So we found the two times the ball is 1 meter above. And so what do we do now? So if you look at the parabola, right, the two different positions, let's say one is here, the other one is there, your Vx is the same, right? Vx doesn't change. It is 24 cosine of 30. So you have your same 24 cosine 30 here, as you do have your 24 cosine 30 here, right? It pretty much doesn't change. And we want to find the velocity. But the problem is the velocity here is kind of like that. The velocity here has to be a negative one, right? It's going down. Remember that? Like in the projectile, when it goes up, the velocity has a vector that points upward. And when it comes down, it gets a negative sign. So basically, if we want to find the velocity vector, is the adding of these two vectors, right? This and this, and you have something like that. And in this case here, this and that, you have something like that. So this is V1, this is the V at the second point, okay? That's the vector. And so what you need to find then is the vertical component of these velocities. And you can find using the equation for velocity. Vy is equal V naught y minus 9.8t. So the first velocity is V naught y is 24 sine 30, which is 12, minus 9.8 times 0.08 seconds, and it's getting messy. And then your Vy, the second one is 12 minus 9.8 times 2.6 seconds. So you have the two velocities. And once you had those two velocity components, this is not a square. This is not a square. Remember, it's the second. I don't want confusion here. So let's take this out. And let me write this here, second. Oops. Vy second. And I would same here. Vy1. Okay. So this is Vy second, and this is Vy1. All right. So to find the velocity at 1, the magnitude of it, square root, and then you do that nonsense, right? Vy1 squared plus v naught x, which is always the same, and the angle we want to find it, this angle here, phi, tangent phi is equal Vy1 divided by v naught x. And then we do the same for the number 2. Just replace these, become 2, right? And this 2. And then you have the 2 velocities. It's kind of a long problem. On a beautiful sunny morning, Taff Newing leaves home and bikes for 50 kilometers. So, oops. That is our east. That is our north. That is our south. That is our west. Taff Newing leaves home and bikes for 50 kilometers, heading 30 degrees north of east. So 30 degrees north of east, and this is pretty much a vector that has this much displacement. And she stops for a water break, then she turns due south for another 25 kilometers scenery route. So this is 25 kilometers, and she's going due south to visit her aunt Kathy. So how far from home does her aunt? So we want to find the magnitude of this vector, right? You want to find the magnitude of B. How do we do that? You take, so if you call this vector A, the first one, and this is vector B, the second one. So A is equal to 50 cosine of 30 I hat plus 50 sine of 30 j hat, and vector B is equal 0. It's nothing in the I component, but it has a negative 25 j hat. So you add those two to get your vector D, and that is going to give you 50 cosine of 30 I hat and plus 50 sine of 30 minus 25 j hat. So if we want to find how far, just square those two vectors. That's all. And take the square root of it. Okay? Sine of 30 minus 25 square. And the square root is all of that. Done. For an extra bonus, determine the direction. So tangent of 5 is equal to this number, 50 sine of 30 minus 25 divided by 5 cosine of 30, and then the problem is solved. If you want to be specific, based on the fact that you might have done a sketch like that, this angle is pretty much north of east, or something like that. So email me if you need any help, or if you don't understand, or I went too fast here. Okay, all right. Good luck. Have a nice holiday.